Antimony is a chemical element with symbol Sb and atomic number 51. A lustrous gray metalloid, it is found in nature mainly as the sulfide mineral stibnite. Antimony compounds have been known since ancient times and were used for cosmetics. Metallic antimony was also known, but it was erroneously identified as lead upon its discovery. It was first isolated by Vannocchio Biaringuccio and described in 1540. For some time, China has been the largest producer of antimony and its compounds, with most production coming from the Zhuangshan mine in Hunan. The industrial methods to produce antimony are roasting and subsequent carbothermal reduction or direct reduction of stibnite with iron. The largest applications for metallic antimony are as alloying material for lead and tin and for lead antimony plates in lead-acid batteries. Alloying lead and tin with antimony improves the properties of the alloys which are used in solders, bullets and plane bearings. Antimony compounds are prominent additives for chlorine and bromine containing fire retardants found in many commercial and domestic products. An emerging application is the use of antimony in microelectronics. Characteristics. Properties. Antimony is in the nitrogen group and has an electronegativity of 2.05. As expected from periodic trends, it is more electronegative than tin or bismuth, and less electronegative than tellurium or arsenic. Antimony is stable in air at room temperature, but reacts with oxygen if heated, to form antimony trioxide, Sb2O3. Antimony is a silvery, lustrous gray metal that has a Mohs scale hardness of 3. Thus pure antimony is too soft to make hard objects. Coins made of antimony were issued in China's Guizhou province in 1931, but because of their rapid wear, their minting was discontinued. Antimony is resistant to attack by acids. 4 allotropes of antimony are known: a stable metallic form and 3 metastable forms. Metallic antimony is a brittle, silver-white shiny metal. When slowly cooled, molten antimony crystallizes in a trigonal cell, isomorphic with the gray allotrope of arsenic. A rare explosive form of antimony can be formed from the electrolysis of antimony trichloride. When scratched with a sharp implement, an exothermic reaction occurs and white fumes are given off as metallic antimony is formed. When rubbed with a pestle in a mortar, a strong detonation occurs. Black antimony is formed upon rapid cooling of vapor derived from metallic antimony. It has the same crystal structure as red phosphorus and black arsenic. It oxidizes in air and may ignite spontaneously. At 100 degrees Celsius, it gradually transforms into the stable form. The yellow allotrope of antimony is the most unstable. It has only been generated by oxidation of stibina at -90 degrees Celsius. Above this temperature and in ambient light, this metastable allotrope transforms into the more stable black allotrope. Metallic antimony adopts a layered structure in which layers consist of fused ruffled 6-membered rings. The nearest and next nearest neighbors form an irregular octahedral complex, with the 3 atoms in the same double layer being slightly closer than the 3 atoms in the next. This relatively close packing leads to a high density of 6.697 grams per cc. But the weak bonding between the layers leads to the low hardness and brittleness of antimony. Isotopes. Antimony has 2 stable isotopes: 121 Sb with a natural abundance of 57.36% and 123 Sb with a natural abundance of 42.64%. It also has 35 radioisotopes, of which the longest-lived is 125 Sb with a half-life of 2.75 years. In addition, 29 metastable states have been characterized. The most stable of these is 120 meters 1 Sb with a half-life of 5.76 days. Isotopes that are lighter than the stable 123 Sb tend to decay by beta plus decay, and those that are heavier tend to decay by beta minus decay. With some exceptions, Occurrence: the abundance of antimony in the Earth's crust is estimated at 0.2 to 0.5 parts per million, comparable to thallium at 0.5 parts per million and silver at 0.07 ppm. Even though this element is not abundant, it is found in over 100 mineral species. Antimony is sometimes found natively, but more frequently it is found in the sulfide stibnite, which is the predominant ore mineral. Compounds. Antimony compounds are often classified according to their oxidation state, Sb and Sb. The +5 oxidation state is more stable. Oxides and hydroxides. Antimony trioxide is formed when antimony is burnt in air. In the gas phase, this compound exists as Sb4O6, but it polymerizes upon condensing. Antimony pentoxide can only be formed by oxidation by concentrated nitric acid. Antimony also forms a mixed valence oxide, antimony tetroxide, which features both Sb and Sb. Unlike oxides of phosphorus and arsenic, these various oxides are amphoteric, do not form well-defined oxoacids and react with acids to form antimony salts. Antimonous acid Sb3 is unknown, but the conjugate base sodium antimonite forms upon fusing sodium oxide and Sb4O6. Transition metal antimonites are also known. Antimonic acid exists only as the hydrate HSB6, forming salts containing the antimonate anion Sb-6. Dehydrating metal salts containing this anion yields mixed oxides. Many antimony ores are sulfides, including stibnite, pyrargyrite, zinconite, jamesonite, and boulangerite. Antimony pentasulfide is non-stoichiometric and features antimony in the +3 oxidation state and SS bonds. Several thioantimonides are known, such as Sb6S10 2- and Sb8S13 2-. Halides. Antimony forms two series of halides, SbX3 and SbX5. The trihalides SbF3, SbCl3, SbBr3, and SbI3 are all molecular compounds having trigonal pyramidal molecular geometry. The trifluoride SbF3 is prepared by the reaction of Sb2O3 with HF. Sb2O3 plus 6HF2 SbF3 plus 3H2O. It is Lewis acidic and readily accepts fluoride ions to form the complex anions SbF-4 and SbF2-5. Molten SbF3 is a weak electrical conductor. The trichloride SbCl3 is prepared by dissolving Sb2S3 in hydrochloric acid. Sb2S3 plus 6 hydrogen chloride 2 SbCl3 plus 3H2S. The pentahalides SbF5 and SbCl5 have trigonal bipyramidal molecular geometry in the gas phase, but in the liquid phase, SbF5 is polymeric, whereas SbCl5 is monomeric. SbF5 is a powerful Lewis acid used to make the superacid fluoroantimonic acid. Oxyhalides are more common for antimony than arsenic and phosphorus. Antimony trioxide dissolves in concentrated acid to form oxoantimonyl compounds such as SbOCl and 2SO4. Antimonides, hydrides, and organoantimony compounds. Compounds in this class generally are described as derivatives of Sb3-. Antimony forms antimonides with metals, such as indium antimonide and silver antimonide. The alkali metal and zinc antimonides, such as Na3Sb and Zinc3Sb2, are more reactive. Treating these antimonides with acid produces the unstable gas stibina, SbH3. Sb3- plus 3H plus SbH3 stibina can also be produced by treating Sb3 plus salts with hydride reagents such as sodium borohydride. Stibina decomposes spontaneously at room temperature. Because stibina has a positive heat of formation, it is thermodynamically unstable, and thus antimony does not react with hydrogen directly. Organoantimony compounds are typically prepared by alkylation of antimony halides with Grignard reagents. A large variety of compounds are known with both Sb and Sbe centers, including mixed chloro-organic derivatives, anions, and cations. Examples include Sb3, Sb24, and cyclic Sbn. Pentacoordinated organoantimony compounds are common, examples being Sb5 and several related halides. History. Antimony sulfide, Sb2S3, was recognized in pre-dynastic Egypt as an eye cosmetic as early as about 3100 BC, when the cosmetic palette was invented. An artifact, said to be part of a vase, made of antimony dating to about 3000 BC was found at Tello, Chaldi, and a copper object platted with antimony dating between 2500 BC and 2200 BC has been found in Egypt. Austin, at a lecture by Herbert Gladstone in 1892, commented that, "We only know of antimony at the present day as a highly brittle and crystalline metal, which could hardly be fashioned into a useful vase, and therefore this remarkable find must represent the lost art of rendering antimony malleable." Maury was unconvinced the artifact was indeed a vase, mentioning that Selim Kunov, after his analysis of the Teo object, attempted to relate the metal to Transcaucasian natural antimony, and that the antimony objects from Transcaucasia are all small personal ornaments. This weakens the evidence for a lost art of rendering antimony malleable. The Roman scholar Pliny the Elder described several ways of preparing antimony sulfide for medical purposes in his treatise Natural History. Pliny the Elder also made a distinction between male and female forms of antimony. The male form is probably the sulfide, while the female form, which is superior, heavier, and less friable, has been suspected to be native metallic antimony. The Roman naturalist Pedanius Dioscorides mentioned that antimony sulfide could be roasted by heating by a current of air. It is thought that this produced metallic antimony. The first description of a procedure for isolating antimony is in the book de la Pyrotechnia of 1540 by Vannocchio Biaringuccio. This predates the more famous 1556 book by Agricola, De Re Metallica. In this context, Agricola has been often incorrectly credited with the discovery of metallic antimony. The book Currus Triumphalis Antimony, describing the preparation of metallic antimony, was published in Germany in 1604. It was purported to have been written by a Benedictine monk, writing under the name Basilius Valentinus, in the 15th century. If it were authentic, which it is not, it would predate Biaringuccio. The metal antimony was known to German chemist Andreas Libavius in 1615, who obtained it by adding iron to a molten mixture of antimony sulfide, salt and potassium tartrate. This procedure produced antimony with a crystalline or starred surface. With the advent of challenges to phlogiston theory, it was recognized that antimony is an element forming sulfides, oxides, and other compounds, as is the case with other metals. The first natural occurrence of pure antimony in the Earth's crust was described by the Swedish scientist and local mine district engineer Anton von Swab in 1783. The type sample was collected from the Sala silver mine in the Bergslagen mining district of Sala, Västmanland, Sweden. Etymology. The ancient words for antimony mostly have, as their chief meaning, coal, the sulfide of antimony. The Egyptians called antimony MSDMT in hieroglyphs. The vowels are uncertain, but there is an Arabic tradition that the word is made amet. The Greek word, sigma tau iota mu mu iota stami, is probably a loan word from Arabic or from Egyptian stm and is used by Attic tragic poets of the 5th century BC. Later Greeks also used sigma tau beta iota stabi, as did Celsus and Pliny, writing in Latin, in the 1st century AD. Pliny also gives the names stimi, labaris, alabaster, and the, very common, platyophthalmus, wide eye. Later Latin authors adapted the word to Latin as stibium. The Arabic word for the substance, as opposed to the cosmetic, can appear as ithmid, athmud, uthmot, or uthmode. Literate suggests the first form, which is the earliest, derives from stimida, an accusative for stimi. The use of Sb as the standard chemical symbol for antimony is due to John Jacob Berzelius, who used this abbreviation of the name stibium. The medieval Latin form, from which the modern languages and late Byzantine Greek take their names for antimony, is antimonium. The origin of this is uncertain. All suggestions have some difficulty either of form or interpretation. The popular etymology, from nu tau iota mu omicron nu alpha k omicron sigma antimonikos, or French antimon, still has adherents. This would mean monk killer, and is explained by many early alchemists being monks, and antimony being poisonous. Another popular etymology is the hypothetical Greek word nu tau iota mu omicron sigma antimonos, against aloneness, explained as not found as metal, or not found unalloyed. Lippmann conjectured a hypothetical Greek word alpha nu theta eta mu omicron nu iota omicron nu antimonian, which would mean floret, and cites several examples of related Greek words which describe chemical or biological efflorescence. The early uses of antimonium include the translations, in 1050 to 1100, by Constantine the African of Arabic medical treatises. Several authorities believe antimonium is a scribal corruption of some Arabic form. Meyerhoff derives it from ithmid. Other possibilities include athimar, the Arabic name of the metalloid, and a hypothetical astimi, derived from or parallel to the Greek. Production. Top producers and production volumes. The British Geological Survey reported that in 2005, the People's Republic of China was the top producer of antimony with an approximately 84% world share, followed at a distance by South Africa, Bolivia and Tajikistan. Zhiquangshan mine in Hunan province has the largest deposits in China with an estimated deposit of 2.1 million metric tons. In 2010, according to the U.S. Geological Survey, China accounted for 88.9% of total antimony production, with South Africa, Bolivia and Russia sharing the second place. However, Roskill Consulting estimates for primary production show that in 2010 China held a 76.75% share of world supply with 120,462 tons. Followed by Russia, Myanmar, Canada, Tajikistan and Bolivia. Roskill estimates that secondary production globally in 2010 was 39,540 tons. Antimony was ranked first in a risk list published by the British Geological Survey in the second half of 2011. The list provides an indication of the relative risk to the supply of chemical elements or element groups required to maintain the current British economy and lifestyle. Also, antimony was identified as one of 12 critical raw materials for the EU in a report published in 2011, primarily due to the lack of supply outside China. Reported production of antimony in China fell in 2010 and is unlikely to increase in the coming years, according to the Roskill report. No significant antimony deposits in China have been developed for about 10 years, and the remaining economic reserves are being rapidly depleted. The world's largest antimony producers, according to Roskill, are listed below. Reserves. According to statistics from the USGS, current global reserves of antimony will be depleted in 13 years. However, the USGS expects more resources will be found. Production process. The extraction of antimony from ores depends on the quality of the ore and composition of the ore. Most antimony is mined as the sulfide. Lower-grade ores are concentrated by froth flotation, while higher-grade ores are heated to 500 to 600 degrees Celsius. The temperature at which stibnite melts and is separated from the gangue minerals Antimony can be isolated from the crude antimony sulfide by a reduction with scrap iron Sb2s3 plus 3 Fe2Sb plus 3 Fe. As the sulfide is converted to an oxide, an advantage is often taken of the volatility of antimony oxide, which is recovered from roasting. This material is often used directly for the main applications, impurities being arsenic and sulfide. Isolating antimony from its oxide is performed by a carbothermal reduction.